Hello everybody and welcome back to Calc 3 Online. Today we're just going to talk about the beginnings of how to write lines with vectors. So something that's going to continue to show up in this course is basically describing the math we're doing using vectors, and an easy kind of place to start with that is with lines. So if you take a line in standard form, maybe 2x plus y equals 0. This is kind of something you're more used to from like algebra 1 even, but I'm going to show you first how to basically take something like this and decompose it kind of in the vein of the dot product. So there is a connection here, and basically we've got a number vector and we've got a variable vector. So really you could kind of think of this thing as the dot product of vector 2, 1, right, dotted with a vector xy. And it would equal the 0 vector here. And this is actually a vector form of a line. They call this the normal form of a line. And it's just normal because the two vectors are equal, or really you should always just think perpendicular. So I was going to kind of sum some of that up over here. So so this 2x plus y equals 0 implies that the vectors 2, 1 and the variable vector xy are just perpendicular, okay? And I can draw it, so now that I have this line, the 2, 1 vector, right, would look like 2 in the x and 1 in the y, which is about right there. And you can see, it's probably not perfect, but that vector is perpendicular to, let me do that one. So this right here, maybe I should do it in red. This right here is the xy vector I was talking about. And basically, the end of that vector can always just kind of end at different variables that would still lie on that line. And any of these red vectors would be perpendicular to the yellow vector 2, 1, right? Because we could move the 2, 1 here, and it's the same vector. And we could move 2, 1 there, and it's the same vector. So those would always be perpendicular. So an interesting question that I want you to think about is this question 1 right here. So how many unit normals are going to be perpendicular to this line in 2 dimensions? So if you think about that for a second, I just drew, really, again, this vector, assuming it's the same length every time. That vector only counts 1 time, right? That is definitely perpendicular, so that's 1. But if you think about it, you could also take, so maybe if I call this n, well, it's probably not a unit vector, so it's not a unit normal, but I could normalize it. But if this was normalized, then the negative of it would also be perpendicular. So in 2 dimensions, there'd only ever be 2 there. And this is something that's going to come up later on. And something that's kind of weird, and it's harder to draw, definitely, but if you think about the line in 3D space, basically, since you could take that, say this is the line in 3D space, I could draw that vector, in a sense, rotated around and around and around that point infinitely many spots, all of these being perpendicular to that line. So in 3D, there would actually be an infinite amount, mostly just because of 100% because of the direction part of that vector. So that's also going to be something that we're going to see down the road, and it's important to kind of keep in the back of your head. So one last thing I want to show you is just how to find something like a normal vector. So if we have this vector for -1, 3, and we want to craft a vector that is going to be perpendicular, right? We want the dot product with that other vector to just be the equal 0 vector. And you can do this really just kind of setting up an easy kind of dot product for you. So you could take the x component to be what we're going to solve for, and then you could let the y component be like a 1, and the z component to be a 1. And if you just solve this out, you basically get a single variable equation to solve. So we know that we want this result to be equal to 0. So 4x plus 2 needs to equal 0. So 4x is -2. Next would be equal to a -1/2. So if you put this back in here, right, you will have crafted one of these kinds of vectors that would be perpendicular. So one of the things that we're going to learn with lines in vector form is we're going to need to sometimes find one of these vectors, and there can be lots of them. And to calculate it, you can just basically set up an equation like that. So one other thing I want you to think about now is if we have the line no longer 2x plus y equals 5, but, no longer 2x plus y equals 0, but this time 2x plus y equals 5, it really is just the original line moved up 5, right? So we would have this line L would go up to 1, 2, 3, 4, 5. It would still have the slope, right? This is all just kind of out of Algebra 1 stuff. And what I want you to think about is, or realize when you see this, is that these vectors that we just talked about, 2, 1, and this like variable vector, these two blue vectors would still be, n would still be perpendicular to this red line, and x would still be parallel. And so I'm going to create another vector. I'm going to create a vector p, which is the vector just, 0, 5. And then I'm going to create a vector capital X, which is just a variable vector on this new line. And if we just work through kind of the vector addition here, right? If we go through X and then we go down through -p, right? The resultant here would still be parallel to our red line. And so then we would know that that would be perpendicular to n also. And you'll see where this is going in a second. So let me draw that. So we're going to go down in P, and then this vector here, right, which kind of comes out of this triangle. This blue vector, I'm going to call, so this is going to be x minus p. And that vector, if you dot it with the normal, it should be, so let me fill in some of these blanks. So this was 0, 5. this was xy, and we know that x minus p is still going to be perpendicular to the normal, just based on the geometry in the picture. And this is is something we can simplify a little bit. So we could distribute that with the dot product there. We'd get n dot x, and then we'd get minus n dot p equals 0, so n dot x would be equal to n dot p. And this thing right here looks kind of weird, but you'll see this from time to time. And this is actually just a fancy vector way to write lines like 2x plus y equals 5. This right here and this right here really say the same thing. This is saying it in the Calc 3 way, and this is sort of saying it in like the Algebra 1 way. They mean the exact same thing. So where we're kind of going with this is we're going to end up calculating normal vectors sometimes, and this is always just an arbitrary variable vector. If it was in 3D, it would be x, y, z, right? And we can do all sorts of problems with this, where we could then, if we knew a point on the line and that we had this variable vector, we could craft a normal and things like that. So right now, I just want you to realize that this and this say the exact same thing. And that's kind of just summed up right here. So I won't really read it again, but you can pause the video and read that, but it just says the exact same thing that I was talking about. So one other thing, though, is that this n dot x equal to n dot p can sort of be understood in another form, and honestly one that I sometimes think is a little more intuitive. So we know that this vector, so this is from the point, I should probably put an arrow on this. So px, I'm saying that vector, which would be the vector x minus the vector p, that has to be some scalar of the direction vector. And the y is simply that it is parallel. So when you have two, so if I go back here, right, like when I take this right here was my x dot p, or x minus p, this has to be a scalar of the direction vector, because that's just what our definition of parallel means in vectors, in vector language. So what we can kind of translate that to is this statement right here. So t is just some element of the reals here. And all I'm saying is x minus p is equal to some scalar on that direction vector. The idea is like if I go back here again, say my direction vector was right here, that was like representing sort of the slope of that line, then the t, to scale it out to this, would have to be some sort of t that's basically bigger than 1, because we know that we are scaling x minus p up to get to d, we're scaling d up to get to x minus p. And if you basically just do substitution, if you just basically add this p over, right, we could form another vector equation for a line that if you just add p over, you would, so we get that. And this is a sort of the vector component form for like any line. Like again, we're just sort of translating things from Algebra 2 into things that are more Calc 3 related. And the way I want you to think about this one is, you can kind of build a line with vectors by starting with a point and then just adding to it, then you add some scalar of the direction. That's direction vector. That's all this thing says right here. And the t can be both positive and negative, and that's why, if I was taking this line up here, right, maybe a positive t of different sizes gets me these new vectors and builds part of that line. I would have to build some part of the line this direction, so I would need negative t values to go that way. But if you let t vary through all reals, you would eventually get the line. And that's what we call, like down here, the vector form of the equation of a line. And that can be in R2 or R3 or R4 or really anything. And you just look at it as point, and then add to that point a scalar of the direction vector. So I just wanted to kind of show you quick how to use this. So we have a line that we want to write in 3D space, and it's got a point that goes through at -1, 5, 0, and another one at 2, 1, 1. And so actually, if you were going to write this vector equation of the line, the x vector, again, is like a variable vector, so I'm going to use x, y, z. And p can just be, doesn't even have to be this p. There's nothing special about this. It's just got to be a point on the line. So I'm going to actually use this one just to change it up. So I'm going to say 2, 1, 1. And then I need to add to it a scalar of the direction vector. And to get this, right, this is basically like your slope, your m from algebra 1 and stuff. And you can just get that by, if you ever are in, any dimensional space and you want to know, what vector goes from this point 1, 1 to this vector, this point over here at 3, 2, how about? You can really just, like, to calculate that vector, right, you just, you just do subtraction of the components. And so we could do, to get this x component, we could do, I'm going to write it over here. So I'm going to go p to q, let's say. And so if I go p to q, I'm going to need to subtract p from q. So, right, if my p is here, my q is here, I take the x component of q and subtract the x component of p. So 2 minus -1 is 3. And then 1 minus 5 is -4. Then 1 minus 0 is, 1 minus 0, I looked at that too quick, is 1. And that would be it. So this becomes something that is actually much easier for computers to understand. It's used in linear algebra all the time. And really, it's kind of the way that people write lines down the road. We end up being more interested in kind of this form, I would say mostly because of how nice computers behave with this. And I thought it was good to maybe tack this on quick too. So you can easily get parametric equations for a line if you have vector form like this. So really, if you just read off every row, so what I mean by that is the first row says x equals 2 plus 3 times t, right? That's the first row. Second row would be y equals 1 minus 4t. And the third row would be z equals 1 plus t. This is parametric, right? So if we let now like t equal, say, 1, right? We know a point on that line. We know x equals 5, y equals -3, and z is 2. And so it's a way where you can, again, this is kind of easiest for computers, we can define this in some program, then go through different t values, and we'll find different points, and then we can sort of start to connect the dots, and we would get a line in 3D. So there's a lot here, but really I just want to make sure you're comfortable with one, parametric equations of lines, which are usually not so bad once you have the vector form, which is another one that's really important. And the other one I want you to know is this normal form. So really just a fancy way here to kind of think back to lines like this. Hopefully you kind of see the connection between this and the dot product. And so that is about it for today.